Okay. Whoops. So these notes are in the Files tab, so hopefully you printed them off already. Okay, so this is something different. We haven't done momentum yet. This is something you definitely did not do in Physics 11, I hope. So yeah, so the word momentum is often used. My 6-year-old son used it the other day, correctly actually, which is surprising. So momentum is like it's like when you say something has momentum, it's hard to stop. That's typically when it would be used, which is kind of correct. But often people say like, oh, something's going fast, it has a lot of momentum, but it's actually a product of mass and velocity, so it depends on both. Okay, and the units, I'll get into the units in a sec. So momentum is the letter P, and it's a vector, is equal to mass times velocity, which is velocity is also a vector. And so this is where we get our kilograms meters per second. So mass is measured in kilograms, velocity measured in meters per second. So when you multiply those together, you get kilograms and meters per second. Okay. So let's just look at an example. So we have a 1,200 kilogram car traveling at 60 kilometers an hour and 12 million flies flying at 10 meters per second. So if you want to compare these two, they have to be in the same units. So we have kilograms and grams, and we have kilometers an hour and meters per second. So let's change this 60 to meters per second by dividing by 3.6. So this is 16.67. And then we'll change this to kilograms eventually as well. So the car, its momentum is 1,200 times 16.67, which is 20,000 kilograms meters per second. Okay. Now, if you have 12 million 1-gram flies, that's a total mass of 12 million grams. So the flies. And then so at 12 million grams, so 12, 1, 2, 3, 4, 5, 6 grams is equal to 12,000 kilograms. Okay, you just divide it by 1,000 because there's 1,000 grams in 1 kilogram. And so then we would go 12, 1, 2, 3 kilograms times 10 meters per second, which is 120,000 kilograms meters per second. Okay, so if you had a car traveling down the road at 60 kilometers an hour and it hit 12 million flies all at once, the car would stop. It would get destroyed. Okay, because 12 million flies have more momentum than the car itself. So interesting how that would work. Okay, so it depends on mass as well. I don't think you've ever have 12 million flies flying together, but that's besides the point. The point I'm trying to make yeah, never mind. Technically, if you hit a fly while you're driving, your momentum changes ever so slightly because the fly has momentum as well. Okay, so impulse. Impulse is a change in momentum. So impulse is actually the letter J. I think it's a lowercase j, equals a change in momentum. So change in momentum is delta P. Okay. So then we would say J equals PF minus PI. And yeah, that's about it. Now, the impulse, I just call impulse delta P. I rarely actually write J. I just write delta P because that's what it is. It's a change in momentum. Okay. Now, if you think about it, in order for momentum to change, so delta P is going to be PF minus PI. PF is going to be mVF minus the initial momentum, which is going to be mVI. because momentum is mv. And so you could go delta P equals m times delta V. Okay, now this delta V suggests acceleration. Okay, so in order for velocity to change, there needs to be acceleration. Okay, now if we take it a step further and apply the dynamics to it, in order for there to be acceleration, there has to be a net force. Okay, so you can actually tie impulse directly into net force, and it works like this. Impulse is equal to your change in momentum. In order for momentum to change, you have to have acceleration, which is caused by a net force times time. Okay, so we can also use net force times time to get your impulse. So there's sort of two different ways to do this. You can either use your change in momentum, or you can use F net times T. It's kind of like when we did work. You could choose to do F times D or change in energy. This is why the units could be Newton seconds. Okay, because forces are measured in newtons, and then we multiply that by time, which is seconds, you get Newton seconds. Now remember that a Newton is a kilogram meter per second squared. So if we take that and we multiply it by a second, this second cancels that second, and you're left with kilograms meters per second. Okay, so a Newton second is the exact same thing as a kilogram meter per second. It doesn't matter which one you use, they are the exact same thing. Okay, so I often use Newton seconds because it's easier to write. Okay, I realize now that this ball doesn't have any mass, but let's say it's 250 grams. Okay, baseball pitchers, the 250 gram ball at 32 meters per second. The batter strikes the ball and it leaves the bat at 48 meters per second. What is the change in its momentum? Okay, now in this case, let's say the pitcher throws the ball this way. Let's try it again. Whatever. So VI is that way, which is 32 meters per second. The VF is going to be that way. Okay, like hopefully most of the time when a batter hits a ball, it goes back towards the pitcher. So the VF is 48 meters per second. Okay, if it goes the other way, the batter is doing something wrong. So in the case of change in momentum, we can deal with M delta V. Okay, this is just the shorthand of what I did up here, where I'm doing PF minus PI, MVF minus MVI, M delta V. Okay, and so this is going to be M, so 250 grams or 0.25 kilograms, times VF minus VI. Now VF is negative 48. Okay, it's going to the left, minus VI, which is positive 32. So it looks like that. And so negative 48 minus 32 times 0.25 is negative 20 kilograms meters per second. I'm going to try use kilogram meters per second because I'm doing mass times velocity. If I was doing net force times time, I would probably use Newton seconds. But again, it doesn't matter. They're the same thing. Okay, so here I get negative. Now that's because I'm assuming that the ball is going to the right first. Had I said this is the VI and this is the VF, my answer would come out as positive 20. Okay, it just depends on how you define your direction. Okay, doesn't really make a difference. Okay, the next little bit, forces and momentum. So this is just a practical part of it. Now, if delta P is M delta V, but it's also F net times T, then there's a relationship that happens here. Okay, so if a student jumps off a desk, when they land, they bend their knees on impact. Why does this help prevent some serious damage to their knees? Well, if you think about a student jumping off a desk, so here's the desk, here's the floor, here's the student. Okay, if they jump off, their velocity at this point, so their delta V will remain constant regardless of how they jump. Okay, they're just falling off the ground, so their delta V will stay the same. Their mass also stays the same. Okay, so that means that this side of the equation will stay the same regardless of anything. Okay, their initial velocity will remain constant, their final velocity will remain constant. No matter how many times the student steps off the desk, that will always be true. It depends on gravity. So if you look at the other side of the equation, in order to keep one side of the equation constant, if time goes up, F net has to go down. Okay, because it's a multiplication. If it, like, it's just a mathematical relationship. If you increase time, force has to go down. And that's the whole point of impact force. Okay, if you can increase the amount of time of the impact, you decrease the amount of force. Okay, if you've ever watched boxing, when a boxer is about to get hit in the face, they'll relax their neck and allow their head to fall back. It's called riding the punch. Okay, because if you can increase the amount of time the boxing glove is in contact with your face, you decrease the amount of impact force. Okay, when guys get knocked out, it's because they don't see it coming and they don't absorb that impact. Okay, and it's a huge force. Some sports require you to follow through with your swing. Why is this important? So in this case, we have m delta v equals F net times t. Now the amount of force, so like I'm going golfing this afternoon. So golfing is one of those follow through sports, okay? The amount of force you can hit the ball with your club is dependent on your muscle mass, your swing. It doesn't, like if you try to smoke it harder, it's not, there's only a maximum amount of force you can give it. So what we say is in a sport like golf or tennis or whatever, the amount of force you can give it is pretty constant. The mass remains constant as well, which means if those two are held constant, if you increase the amount of time, what you're doing is you're increasing the amount of velocity. Okay, because if you increase one side of the equation, you have to increase the other side of the equation. So that by increasing the amount of time that the racket is in contact with the ball, you're actually you're increasing the change in velocity, which is good. You want to hit it faster. Okay. And then these ones don't, I guess I will talk about those. So number 3, when I learned how to drive, I learned how to drive in like this boat of a car that was really rigid. And if I got into an accident, it probably wouldn't have been good. But back in the day, we used to build cars that could get into accidents and then the cars were totally fine. Okay, now if you are an fender bender, your cars are right off because it's totally destroyed. Okay, that's not the way it used to be. And we used to make them strong because, like, think about a tank, right? You're in a tank, you think you're safe and you can hit anything, whatever, you're good. Okay. But it's actually counterintuitive because if you hit a car, or let's say you're in a car and you hit a tree, and it's not, your car doesn't crumple, the impact time is very, very quick. And if it's quick, the amount of impact force is really high. Okay. So we designed crumple zones in cars. So now when a car hits a tree, the car will actually smush, which actually, it acts like a spring almost. It absorbs the impact. Okay. It increases the amount of time, decreases the amount of force. Okay. An airbag does the exact same thing. A seatbelt does the exact same thing. Okay. They're all designed to increase the impact time. So there's some physics for you. Okay, let's think about number 4 now. Last kind of practical one. A beanbag and a bouncy ball of equal mass are dropped from the same height. So we have a beanbag and a bouncy ball. The beanbag is brought to a stop in the same time that the ball is in contact with the floor. So the beanbag hits the floor and stops. V equals 0. And VI equals, well, also 0. But so let's think about right before it hits the ground, it has a VF going down like that. And then VF will technically be 0. So we'll take this, like Okay, let me explain this a little bit better. Right before it hits the ground, it's going to be moving down towards the ground, okay? And then eventually it's going to stop because it hits the ground and stops. So the VF based off of the height it falls from, so if I were to like VI is 0, A is 9.8, D is whatever the height is, VF is whatever, you can use kinematics to solve it. That's your VI of the ball when it hits the ground. Okay, so the VI of the contact with the ground, and then VF is just 0. Okay, if you think about the ball hitting the ground, the VI with which it hits the ground with is going to be the exact same as the beanbag, but instead of the VF being 0, a bouncy ball bounces back up. So the VI looks like this, but the VF looks like this. Well, the VF's not bigger, but VF looks like that. Okay, whereas in this case, your VI looks like this and your VF is 0. So if you think about the two different changes in velocity, the change in velocity of the beanbag is only this line. Okay, VF minus VI, 0 minus VI is that. The change in velocity of the bouncy ball is this, where you add the VF and the VI. Okay, so it's a much bigger V change in velocity, therefore it has a greater force on the floor. Hopefully that made sense. We've done vector addition and all that, so hopefully you can apply that. Okay, so let's do some examples. A 115 kilogram fullback running at 4 meters per second east is stopped in 0.75 seconds by a head-on tackle. So in this case, calculate the impulse. So impulse delta P is equal to m delta V. Okay, and in this case, our VI is 4 meters per second, and our VF is 0. So in this case, we're going to go 115 times 0, that's our VF, minus 4.0, which is 460 kilograms meters per second. Okay, that is the impulse felt by the tackler. By the fullback, sorry. What is the impulse felt by the tackler? So, oh, sorry, this is negative. There we go, because it's 0 minus 4. It's negative. So the fullback loses speed, so he actually stops. Therefore, his impulse is negative because he's slowing down. If you think about, there's no information about how fast the tackler was running or anything like that, but we can apply Newton's third law. Okay, Newton's third law says that any force will have an equal and opposite force. So the force required to stop the fullback is going to be the exact same force experienced by the tackler. Okay, a tackler cannot tackle somebody with a certain force without feeling that exact same force. Okay, so the tackler's impulse is positive 460 kilograms meters per second. Okay, because it's equal and opposite, Newton's third law. And then we can use that to find the net force exerted on the tackler. So if 460, well, I'll do it this way. Delta P, the impulse, is F net times T. Okay, if that's 460 on one side and F net times 0.75 on the other side, 460 divided by 0.75 is 613 newtons. Okay, and if you think about this, the fullback is running that way towards the east. The force that the tackler applies on the fullback who's running that way will be that way. So this is the force of the tackler on fullback. Well, equal and opposite forces, the force that's felt by the tackler is going to be the opposite. Fullback on tackler. Okay, and that's why it's positive 613 newtons and not negative. Hopefully this is making sense. It's hard not in a classroom. I just want to say that. It's much easier to gauge student understanding when I can see everyone. Oh well, not going to complain about that. Okay, so this is, I called this like momentum in one dimension, but we're going to add in a 2-dimension just to get used to adding in angles, but this isn't a hard one. It's still 90 degrees. A 1250 car traveling east at 25 meters per second turns and heads north and continues on at 15 meters per second. What is the impulse of the car exerted while turning the corner? Now, keep in mind that impulse is going to be m delta v. Okay. Now, in this case, your delta v is going to be, it's going to be different. It's going to be a vector diagram. Okay. So this is our vi. Vi is 25 meters per second to the east, and then it turns so that its VF is 15 meters per second to the north. And so if you, this isn't my diagram because remember that delta V is VF minus VI. So technically it's going to be VF, which is 15, minus VI, so I'm adding the negative, 25, and this is my delta V right here. Okay, so delta V is going to be 25 squared plus 15 squared, square root, squared plus 15 squared, 29.15. And then angle is going to be 25 divided by 15. Whoops. 25 divided by 15. Second tan. 59 degrees. What is that? West of north. Okay, so that's my delta V. And then all I have to do to turn that into a change of momentum is multiply that by my mass. Okay, so my delta V is this right here. This is delta V. So all I need to do is multiply that by 1250. So 1250 times 29.15. And I get delta P, my impulse, is going to be 36,437 kilograms meters per second. And then 59 degrees west of north. Okay, and if you think about it, if a car starts going east and turns north, it needs to stop going east and start going north. So this part of like this x component is stopping it going east, and this part is starting it going north. Okay, so that's why it's west of north. Okay, and not this diagram here. So you have to be careful with your vector diagrams. Okay, so that is our answer right there. Okay, oh man. Yeah, we'll do it. Force times time graph versus time graph. So impulse is, delta nothing, delta P is F net times T. So if you have a force time graph, the impulse would be the area under the curve. Okay, so if I have a line like this, the area underneath is going to be force times time, but that's area, right? Length times width is area. So you can use that to approximate forces acting on something, because forces don't happen constantly. Okay, if it starts off low and then it maximizes and then it gets lower again. So it's not a constant boom, there's your force. Okay, so what we do without calculus or anything like that, we approximate the amount of force. So that's the area under the curve. And then we would say this area over the curve is roughly this shape plus that shape. And so now we have this nice little box here that we can find the area of. And that's how we figure out the average force times time. Okay, we won't get much into that, but this is definitely what you see in university. So it's there to get you prepared for that type of stuff. Okay, calculate the impulse experienced when a 40-kilogram girl lands on the ground from jumping off and by jumping off, I just mean stepping off, a 0.80 meter table Find the average force of her feet on the ground, blah, blah, blah. Okay, so impulse experienced. What we're going to need is, so she's going to step off the table. This makes it look like it's a really big table. Perfect. And this is 0.80 meters. So her VI is 0. Her displacement will be negative 0.80 meters because she's falling 80 centimeters. A is negative 9.8 meters per second squared. We can find her VF right before she hits the ground. Okay, we're going to do that using VF squared equals VI squared plus 2AD. Now, we don't have to do it this way. We could do it with energy as well, but might as well do it this way because I started already. So that's 0, VI is 0, so that just goes away. 2 times negative 9.8 times negative 0.8, forget the squared, 2 times 9.8 times 0.8, and then we're going to square root that. And then VF will equal negative 3.96 meters per second. Okay, now why do I need that? We want to know the impulse experienced when she lands on the ground. Well, when she lands on the ground, her velocity right before the ground is that way, and then her VF will be 0. Okay, so her actual change in velocity will be 0 minus negative 3.96 meters per second. Okay, and that's negative, so that's just, times her mass, 40. Oh no, I'm just doing delta V. So that means that this is going to be 3.96. That's her change in velocity. Okay, and then for her impulse, we can go 40 times delta V, 3.96 times 40. So this is going to be 158 kilograms meters per second. Okay, so that's how we get her impulse when she lands on the ground. So we have her initial velocity right before the ground. When she lands on the ground, it's going to stop. So her VF is 0. We get our delta V. We multiply that by our mass to get momentum. Now for the next part, what is the force on her feet if she absorbs the fall by bending? Oh man, I did this wrong. I thought those were times. Oh well. If we want to do it this way, oh man, I wish those were times. They're supposed to be times. Oh well. If we do it this way, so the momentum change is going to be the exact same. The velocity change is going to be the exact same. So the best way to do this is just to apply kinematics again, where our VI is negative 3.96, our VF is 0, and then add in the distances. If it's 1 centimeter, that's 0.01 meters. And then we can find our acceleration, times that by mass to get your force. Okay, and we'll do that twice. That's the best way to do it. We're not going to deal with F net times T or anything like that. You could apply that here where it's saying, okay, like, let's find the time and then just go F net times T, but that's an extra step. You might as well just find the acceleration times by mass. That's way easier. Okay, and then the other one is going to be VI is negative 3.96, VF equals 0, D equals 0.5 meters, and then find your A. Okay, so it's going to be a lot more force here than it is here. I'm not going to solve it because I think I'm done. Done with this section. Okay, any questions about momentum? It's all linear right now, so it's not, there's no curveballs. It's not that difficult yet. It's going to get harder though, because delta V's don't have to be linear. They can be angles and vectors and stuff like that. So that's why vectors are so important. Oh, where's that called? What formula did I use for the 0 minus? Oh, okay. So right before the girl hits the ground, her velocity is going to be 3.96. And then when she hits the ground, she's going to stop. So this is VF minus VI. That's the formula. So her VF is 0, and then her VI right before is negative 3.96. So it's, you just add it together. This is her delta V right here. When she hits the ground, it's not for when she's falling. There's two distinct motions here. One when she falls and one when she hits the ground. I hope that answers your question. Okay. Dang it, stop. Any other questions?
I was wondering if you could just go over some questions from the worksheet.
Sure. Go for it.
Could you go over number 4 and 11?
4 and 11. This is number 4 right here.
No, it's the law of conservation of energy. The next one.
Right. Number 4 and 11. Okay, perfect. Okay, number 4 first. A safe is hurled down from the top of at a speed of, what is velocity as it hits ground? Okay, so if you think at the top of the building, it's going to have, the safe has EP up here. And typically, if you were to drop a safe, its VI would start at 0. But because it's being thrown downwards at a speed of 11 meters per second, it also has EK. Okay, so it's going to have EP plus EK at the top. And then at the bottom, it's only going to have EK. Okay, so then we're going to go MGH plus 1/2 mv squared at the top equals 1/2 mv squared at the bottom. So m's can cancel out. 9.8 times 130 plus 1/2 times 11 squared equals 1/2 v squared. So 9.8 times 130, 1274 plus 0.5 times 11 squared, 60.5 equals 1/2 v squared plus 1274 times 2 square root. And you get 51.7 meters per second. Hopefully that answer is somewhere like that. Yeah, 52. Okay, so because it's being thrown downwards as well, it has EP plus EK. Okay, number 11. Okay, the pendulum is 1.2 meters long. If the pendulum is pulled until it makes a 25-degree angle, what is the speed of it when it's dropped? Okay, so in this case, we need to draw out kind of what it looks like. So when it's just hanging, it's 1.2 meters long, so 1.2 meters. And then it's pulled this way. It's still 1.2 meters. Oops. Okay, from here to here. And this angle is 25 degrees. Okay, so what we need to do is we need to figure out this distance right here, x. Okay, and we can do that by using the angle and this as our hypotenuse. Okay, so if we kind of complete the triangle like this, that's a right angle. And then from here to here, that's adjacent to that side. So I would go cosine 25 equals, we'll call this A, equals A over 1.2. And so A would be 1.2 times cosine 25, which is A is 1.09. And so that means that A is 1.09, and from here to here is 1.2, which means that this section right here is 1.2 minus 1.09, so this is 0.11 meters. Okay, and so that gives us the vertical drop, or how high the pendulum is above its equilibrium position. So at this point, when you pull the pendulum up to this point, it's going to stop. So V equals 0 at this point. So there's no kinetic energy. But when you let go, it's going to start swinging, which means that there's potential energy here. Okay. And then when it reaches the bottom of its motion, the EP will be 0 here, but it will be moving. So it's going to have EK. And so the EP at this point right here will equal the EK at this point right here. Okay, so it's just mgh equals 1/2 mv squared. M's 9.8 times our height, which is 0.11 meters, equals 1/2 times v squared. 9.8 times 0.11 equals times 2 square root 1.5. 1.5 meters per second. Okay, does that make sense? You just have to do a little bit of geometry.
Yeah, I got it. Thank you.
Okay. Okay. We're not doing this. You can do, I'm going to circle all the questions you can do. That one, that one, that one, left, left, that one, and that is it for that, and then this worksheet right here. Okay, so you can do the first 4 questions of law of conservation of momentum. I don't even know why those questions are there. It's actually impulse. And then you can do worksheet 4.3 as well. And tomorrow, I forgot about that quiz. Okay, I gotta post that energy quiz. I'll do that today still. Once we hang up, I'll post it. So check your OneNotes again for the energy quiz that's coming up. So it's not like it's not going to be worth as much as a test, but it's still an assessment so that I know we're all on the same page for energy. And then tomorrow, I guess we'll meet at 8:30 again. Just trying to figure out what we should do. No, the quiz is only going to be energy, no momentum. It'll be conservation of energy as well, but not momentum. We need to do 2-dimensional impulse and collisions. So maybe, plus you have your quiz. Maybe we're just going to do the 1 lesson tomorrow. So we're just going to do 1 lesson. We'll do it at, what time do I want to do that? Let's do it at 9:30. Let's do it at 9, just in case I want to do other stuff. Okay, so tomorrow's lesson will be at 9. And it's 2-dimensional impulse, so that's it. Okay, so check your OneNote for your quiz, and you can also check the quiz will be due tomorrow by midnight, like before the weekend. What was I gonna say? Oh yeah, check your OneNote for the quiz, and then do the worksheets the questions that I circled, and that's it. Any other questions? When do we get our progress report? Progress reports come out next week, I think, next Wednesday. And I think at this point, if you withdraw from the course, you get a W on your transcript, which it just says that you withdrew. It's not negative or anything like that. Anything else? How exactly the quizzes and tests weighed? I have no idea. I have no idea. It depends on if we actually do a lab or, yeah, we're just gonna have to play it by ear. But seeing as how I can't, like, we can't do as much as normal, so it's just gonna be, I'm just playing it by ear this year because I'm not set certain things because everything changes this year. So no, we're not gonna have a final. No, that sounds like a terrible idea. Yeah. And like the last day, it's like our report cards are probably going to be due on the Thursday. So like we typically don't, we're going to be finished early. Like your last thing will probably be on Wednesday, and then I might teach you something on Thursday just to kind of finish, or yeah, kind of show you what we didn't get to, because we're not going to get to everything in Physics 12. So yeah, we'll get to that point when we get there. We still have lots of time. Well, 2 more weeks after this one, I think. But yeah, we'll get there. It's all good. Okay, I'm going to sign off then for today, and just keep an eye out for that quiz. Any questions, just send them to me. Okay. Have a great day.